Hey everyone, and welcome to this explainer. Today, we're staging a massive heavyweight showdown between two absolute foundational giants in C programming, arrays and linked lists. Now, we're not just going to look at simple syntax here. No way. We're going way beyond that. We're pulling back the curtain to look at physical memory layouts, the brutal reality of speed trade-offs, and we're even going to dive deep into the CPU cache to find out which of these structures is the true heavyweight champion. It's a wildly fascinating comparison, and by the end of this, you're going to know exactly how your computer handles data behind the scenes. So let's get into it.
Before we really get into the weeds, we got to remember the golden rule of computer science. There is absolutely no such thing as a best data structure. There's only the right tool for the specific job you're trying to do. Okay, let's dive into this. On the left side here, we have the array. An array stores items in a beautifully contiguous, sequential block of memory. Think of it like a neat row of sequentially numbered mailboxes right on a street. Now, over on the right, we've got the linked list. Instead of that nice, neat row, a linked list just kind of scatters its nodes completely randomly throughout memory. To keep the whole thing organized, every single node contains a pointer, basically a little directional sign that connects it forward to the very next node.
Think about how we actually interact with these concepts in the real world. An array? Well, it's a lot like an apartment building or a shoe shelf. You know exactly where Unit 3 is, right? Because it's right next to Unit 2. You can just reach out and grab it. A linked list, however, is way more like a treasure hunt or maybe a roller coaster. You can't just skip to the end of a treasure hunt. You have to start at clue number 1. Which tells you where clue number 2 is, and so on. Or think of a roller coaster. You've got to walk all the way from the very first car just to reach the fourth one.
So this is our first major battleground. We're pitting instant mathematical formulas against sequential searching. And when it comes to accessing data you've already stored, the array is the undisputed speed champion. I mean, arrays give you instant O of 1 access time. You want the 100th item? Boom, you're instantly there. Linked lists, on the other hand, suffer from terribly slow O of n access time. Because the nodes are scattered everywhere, you absolutely cannot skip ahead.
Let's actually look at the math behind the array's blazing speed. See, the C compiler doesn't search an array, it calculates. It uses this super fast formula. It takes the base memory address, adds the index you want, and multiplies it by the size of each element. It's pure instant math. But finding a node in a linked list? Yeah, there's no formula for that. You have to start at the head node and painstakingly follow those pointers, one by single one, until you finally reach your destination.
To put that into perspective, let's see how this plays out in actual C code and physical memory. Say our array starts at base address 1000, and we're storing integers. Those take up 4 bytes each. If we want index 3, the compiler instantly calculates 1000 plus 3 times 4, which is 12. So bam, address 1012. It jumps there instantly. Zero searching required. But notice the linked list traversal logic. If that linked list has, say, 10,000 elements, accessing the very last one requires the computer to execute a grueling 10,000 sequential steps of pointer hopping. That is a lot of work.
Okay, so arrays totally win the speed race for finding data. But in this round, the dynamic flips entirely. We're going to see how the array's greatest structural strength, that contiguous memory we talked about, actually becomes its absolute worst operational enemy. Inserting data at the beginning of an array is agonizingly slow. Think about inserting a new person at the very front of a super crowded row in a movie theater. You can't just put them there. Every single seated person in that row has to stand up and awkwardly shuffle one seat to the right just to make room. That is literally what an array has to do. It has an O of n insertion time at the beginning because it has to shift every single element one memory slot over.
To really grasp the scale of this, imagine you have an array with 1 million items, and you just want to insert a single new element at the front. Your computer has to execute 999,999 sequential shifts before it can even place that new piece of data. I mean, that creates a massive, massive performance bottleneck in your software.
Now, what's really interesting about this slide is how elegantly the linked list solves this exact problem. Because the linked list is totally disconnected in memory, inserting at the beginning is as simple as adding a new engine to the front of a train. You just drop the new node into literally any available spot in memory and change the front pointer to hook it up. The rest of the train doesn't move an inch. The whole thing happens in constant, O of 1 time.
If we look at the C code, this pointer swap is beautifully simple. For a linked list, you just create a new node, you point its next pointer to the old head of the list, and then you update the main head pointer to your new node. That's it. 3 fast steps. And here's the real magic. Those 3 steps are exactly the same whether your linked list has 10 items or 1 million items.
This is where things get really fascinating, because we're looking beyond the theoretical big O notation to uncover the physical hardware costs. Like, what is actually happening inside your computer's silicon when you choose one of these structures? Let's talk about memory footprint. Arrays can be really wasteful. If you pre-allocate space for 1,000 items but only use 10, you're just wasting 99% of that memory block. Linked lists never waste unused space because they grow dynamically. But, and this is a big but, linked lists charge a pretty hefty pointer tax. Every single node has to carry the actual data, plus the pointer to the next node. On a modern 64-bit system, that pointer alone is 8 bytes. So if you're storing a tiny 4-byte integer, the node actually takes up 12 bytes. That means a linked list uses roughly 3 times more memory to store the exact same list of numbers.
And that brings us to an advanced but absolutely crucial concept for modern performance, the CPU cache. This is a tiny, microscopic layer of super-fast memory physically built right onto the CPU processor chip itself. Fetching data from your system's main RAM is incredibly slow for a processor. To run fast, the CPU desperately wants to work out of its cache. Think of the CPU cache as the desk right in front of you, and main memory as a slow filing cabinet all the way across the office. Arrays are amazingly cache-friendly because array data is contiguous. When the CPU fetches index 0 from the filing cabinet, it grabs a whole chunk of the surrounding memory, indexes 1, 2, and 3, and just dumps them all on the desk at once. The next few reads are instant. Linked lists, however, they're a nightmare for the cache. Because the nodes are scattered randomly in memory, the CPU grabs node 1, puts it on the desk, reads the pointer, and realizes, uh-oh, node 2 isn't on the desk. This is a brutal cache miss. The CPU literally has to walk all the way back to the slow filing cabinet for every single node.
Now we're going to synthesize all of this theoretical math and hardware trivia into a highly practical, earned cheat sheet for your real-world development projects. So the crucial point is right here in this master matrix. When you need to rapidly access elements in the middle of a dataset, arrays completely destroy linked lists. But when your application requires constant inserting or deleting of data right at the beginning of a dataset, the linked list entirely dominates the array.
Connecting these concepts to reality, we can map them directly to actual applications. Arrays are absolutely perfect for things of a known size that require heavy sequential math, like rendering thousands of pixels in an image on your screen, or maybe calculating averages on a fixed table of monthly sales data. Linked lists, however, really shine when things are dynamic and frequently shifting. Think of a music playlist where you're constantly queuing up new tracks next, or the undo feature in a text editor, where you're constantly stacking and unstacking your most recent typing actions.
To make it dead simple, let's walk through this final rule of thumb flowchart. Ask yourself, do you need instant access by an index number, or is your system's memory extremely tight? If yes, use an array. Do you have absolutely no idea what the final size of your data will be, or do you have a ton of insert and delete operations happening constantly? If yes, use a linked list. It really just comes down to mapping the physical constraints of the data structure to the functional requirements of your software. Before we wrap up, I want to leave you with a provocative thought to test everything we've just covered. If you were sitting at your desk today and you were tasked with engineering the back button history for a brand new web browser, knowing that pages are constantly added dynamically as you browse, but you mostly only interact with the most recently added page, which data structure would you choose to build it and why? Think about the speed, the memory, and the access patterns we talked about. I really hope this explainer has left you fully equipped to answer that and eager to write some highly optimized code. Thank you so much for joining me on this deep dive. Keep learning and keep building.